That's where this inspiration came from. So the percent concentration, and I gave you 2 grams, like meaning the units of grams twice. So it's mass over mass, right? So it's pretty simple. You would have your small number divided by your big number times 100, right? Yep, so it's pretty much 75, except for it's 1 over, so 7.5%. We okay with that? That should hopefully be really easy. On these percent concentrations, don't overthink them. They are easy. Okay, parts per million. You can take it in 2 ways. 3 over 40, and then times that by 10 to the 6th. Right? What do you do, or what do you get when you get that? 75,000. Okay. The other way, and you don't have to do it the way I do it. It really doesn't matter. You convert this to milligrams, which is 3,000 grams. You convert the one to kilograms, which is 0.04, and you should get 75,000. Why do I do it that way? Just because that's the way I learned it, and I've always done it. So it doesn't matter. Whichever one you find to be easier, do it that way. A lot of times parts per million will be given to you in milligrams and kilograms. So that's why I just have always stuck with that. Okay, are we all right with both of those? Who was successful? Both of them. Raise your hands. Look at that, kids. We have turned the corner. This class is easy now, right? Well, that's true. This is the last easy section we have. I think I already said that. All right. These are the last ones that are on the test that you have not seen yet. Will you take a minute? There's 3 of them there. So maybe a minute each, and then we'll decide. All right, the phrase likes dissolves likes referred to the fact that solvents can only dissolve solutes of similar molar mass? No, definitely that's just dumb. Gases can only dissolve other gases? No. Polar solvents dissolve nonpolar and vice versa? That's wrong. Condensed phase can only dissolve other. What is that? Polar solvents dissolve polar solvents and non-dissolve that, right? Like bonds will dissolve in each other. Unlike bonds will not. An unsaturated solution is one that has no double bonds. That actually is going to get someone. If that's on like the real AP test, you're like, oh, that's so easy. That's A. Because an unsaturated fat or hydrocarbon has no double bonds, but this is a solution. All right? Does it contain no solute? Has a concentration lower than the solubility? That one sounds probable. Contains more? No. Contains the maximum concentration of solute possible and is in equilibrium with undissolved solute. That's saturated, so it has to be this one. That did sound right. We just wanted to double check the other two. You okay with that? Okay. Pressure has an appreciable effect on the solubility of gases. Henry's law. All right. The solubility of a gas is directly proportional to the pressure above the gas. Liquids and solids can't really be pressurized, so like you can squeeze them, but that doesn't really affect them at all, and especially it won't affect the type of solution they're in. Okay, you okay with that? Okay, we've now seen every multiple choice. I think there might be 1 or 2 that were similar to others that I didn't pick, but I'm pretty sure I have all of them. All right, so the next thing we're going to talk about is mole fraction, and mole fraction is not bad because we've done it before. We had to do mole fraction when we found partial pressure. Sound familiar? Okay. Now, this would be in a solution, so it's a little bit different. But it would be the moles of A, or whatever thing you're talking about, divided by the total moles in the solution. All right? You will need this when it says, in some applications, one needs the mole fraction of solvent, not solute. Make sure you find the quantity you need. So just make sure you read the question carefully to answer whether it's asking for the solution or the solvent. Okay, so mole fraction, example of that would be like 20 grams of salt in 200 milliliters of water. We should be able to find the mole fraction for NaCl and the mole fraction for H2O. It's a fairly simple process once you've seen it. So we first need to convert everything into moles. You okay with that? So 20 grams of NaCl, 20 grams for every 58.5 grams, there's 1 mole. So I take 20 and I divide it by 58.5. You have that, Isaac, already? 0.342 then. Sound good? I gave every chemistry A test to that kid the other day. Okay. All right. Now, that's for NaCl. What do you do with the water? Because it's only in milliliters. All right. Good. The density is 1 gram per milliliter. So it's 200 grams of water. The molar mass of water is 18 grams per 1 mole. 11.1. The mole fraction for salt then, I take 0.342 divided by the total of these two, which is 11.42, right? .442? Sorry. Okay, what does that equal? Okay, 0.029. All right. X, or mole fraction, or ratio, they're the same thing. For H2O would be 11.1 divided by 11.442. Is that what you... Okay, those are my 2 mole fractions. They should equal 1, and they're really close, right? Like we're 1/100th off. But those 2 should add to 1. When Kitzel told me this, it was 0.0298, so really I would have rounded that 0.03 if I hadn't already written it 2. That'd be perfect. Okay, we've done it before. Are you okay with that? Okay, let's just do one tiny thing. We won't change any math, but we'll say, what is the mole ratio of the solute? Okay, so make sure that you know which one's the solute and the solvent. The mole ratio of solvent was that 0.97. I'll just call that 0.03. So just remember which piece is which, and that the math will matter sometimes. The solute is always going to be the smaller number. Why is this not going away? There we go. Okay. So all the math hopefully was easy so far. There was just a lot of little parts. So far, percent concentrations, parts per million, and now mole fraction. So far okay? All right. Next is molarity. Once again, this is something we've done before, so hopefully you'll feel just fine about molarity. You will recall this concentration measure from Chapter 4. All right. Because volume is temperature dependent, molarity can change with temperature. This is not on your test, but I remember seeing it on last year's AP test. And I was like, you know what, you dirty dogs. That is such a minute thing to actually test. But it was on there. Okay? It gave like 5 different units of volume, or not volume, of concentration, and it said which of the following is temperature dependent? And molarity was the answer, because the temperature can change the density, which can change the volume, and yada, yada, yada. But anyway, so it's moles of solute per liters of solution. Now, molarity is really never given to you in moles of solute. It's always given to you in grams. So you always have to do a tiny bit of math. All right? So it'd be, we already have this number. So 20 grams of NaCl in 3 liters. Okay, 3 liters, and there's your molarity. Okay, so hopefully by chapter 13 in an AP class, you're comfortable going from grams to moles. That is super basic. Tying your shoe, you have to use it all the time. All right, so when you divide this, what's that? Molarity is the unit of capital M. Capital M means moles per liter. Mole fraction, you might have noticed there was no unit because there is no unit. Okay. We all right with that? Okay. So there's our fourth thing of math. Now remember, on the exam, I'll put most of these equations up. So you don't have to memorize, you need to know how to use them. All right, now molality is the new one, and it's the main one for this unit. Molality is moles of solute over kilogram of solvent. All right? Because both moles and mass do not change with temperature, molality, unlike molarity, is not temperature dependent. Molality and molarity are exactly the same in one instance. Do you know what that is? If your solvent is water. How come? All right, 1 liter of H2O is equal to 1 kilogram of H2O. Based on that density, 1 gram per milliliter. Okay? Now, when molarity gets different is when you have a different type of solvent, or they'll tell you the density of the solvent, and then you have to do a little bit of math, and most likely that's coming up next. All right. Oh, by the way, it's shortened up with molal, in case you care. So there's a molar. Molar is short for molarity. Molal is short for molality. And when they describe the solution, they would say you have like a 2 molar solution, or you have a 2 molal solution. You okay with that? All right. So this problem, let's not worry about it. Let's say we have 20 grams of salt. We'll just stick with that because we already have that number. Dissolved in 300 milliliters of methanol, which is H3OH. Okay, and then in these problems, if you are solving for molality, you must know the density of the solvent. The problem has to tell you. We'll say the density is 0.92 grams per milliliter. Oh, hey, that's a really big M, but whatever. So the question would then say, what is the molality and what is the molarity? Okay, so let's do molarity first since we're used to that. Molarity is just moles per liter, correct? Okay, now I didn't change anything. We've had this number for a while. NaCl, is that 0.341? 342. Okay, that's the moles of salt. Okay, which is just 20 divided by 58.5. Okay, we did that the last few problems. Okay, so molarity is moles, so 0.342. How many liters? 0.3. So we end up with 1.14 capital M. Who's with me so far? Okay, I seem to have lost 10%. So just remember the units. Moles per liter. To convert moles from grams, you take the mass I gave you and divide it by the molar mass. Okay, so now molality is slightly different. The numerator is the same. It's still 0.342. But I need to find the mass of this. Right? Okay, so I'm going to go way old school here. Density is equal to mass over volume. Correct? You remember that circle from months and months and months ago? Which one do I want to solve for? The mass. So I cover up M. What am I left with? D times V. My density is 0.92 per milliliter. So I'm going to take this. It's already written, so I'll just put it there. And I'm going to multiply it by 300 milliliters. Senor Rasmussen. She's super pumped. She's been doping hard, though, for the region, so hopefully she passes. You don't even know what blood doping is. It's actually genius. I'm sorry. It's genius. All right, what was your question? It can be in milliliters, that's fine. As long as the thing's in grams, that's all I need. I need these to match. It wouldn't because you then have to move the decimal anyway. Because it would be like 0.00, no, it'd be 92 grams or whatever. You would just have to move the decimal. Okay, when you multiply this, what do you get? 276? That's 276 grams. But we need it in what? Kilograms. So that's 0.276 kilograms. You okay with that? And that goes down here. And then I can find the molality of my solution, which will be close, but it is different. 1 point what? Okay. We okay with that? Should we do another one just like that? Okay. All right. So, let's say you have 75 grams of IF in 500 milliliters of propanol. And let's say the density is equal to 1.18 grams per I want the molal and the molarity. Okay, give that a shot. So the first step would be to find the moles of your solute. 75 over 26, right? So that's 3 point something. Or 2.9. Sorry, went the wrong direction. All right, whatever. 2.9, I already wrote it. We're going to call that good. All right, so that's going to be your numerator in both. 2.9 over that, 2.9 over this. All right, molarity, that was the easiest one. So 0.5 on the bottom, and you end up with 5.8. All right, then we need to find the mass of these 500 milliliters. So I take my density and I multiply it by my volume. This is in milliliters, so this can be in milliliters. 500 milliliters, those cancel out. And what do you end up with here? 0.590. Okay, so that comes down here. Oh yeah, thank you. So that's grams, must be in kilograms, so 0.590. You put that down there, and what do you end up with here? 4.9. Okay, sounds good enough to me. Whoa, screw you people. There you go. It doesn't even look like I cheated at all. All right. Are we okay with that? All right. I've never written one out like this, but you should know how to do this, so we'll work through it together. Yeah, like there's one tiny application left, but this is the majority. I don't know how to write it. All right, let's see. You have a 17% solution of LiCl. And we'll just go methanol again. CH3OH. Molarity. I need to give you the density still. Molality. And what did I give you for density? Well, it doesn't really matter. I just made it up anyway. 0.91-ish. Okay. This ties percent to what we did, like what we did yesterday, to what we're doing now. Now this is, when you see one of these, and I remember seeing these years ago, I was like, I don't know how to do this problem. He didn't give me a volume. All right? But I don't have to. Because no matter what volume I give you, 17% of that substance is your solute. Are we okay with that? So you could do 10, 100, 1,000, 500, 200. It doesn't matter what volume you choose. I would choose 1,000. It doesn't really matter. It really doesn't matter because we're not using water. But whatever. I'll just go with 1,000. You with me so far? If I have percent and I have 1,000 grams of this, 170 grams of it are what? All right, that's my LiCl. Then 830 of them are what? Are methanol, CH3OH. Now, what would I do with this data? I could find my molality, piece of cake, right? The molality, I take 170 and I divide it by 26. What does that end up being? Oh, it's not LAF anymore. Sorry, I switched it to LICL. I wasn't paying attention. What's that? 42. Thank you. I forgot. Well, that's interesting. She's not here. Which they do down there, don't they? Yeah. So find the test. The drug. Not much. I don't have anything. If you remember, on the previous problem, I did LIF. And that is 26, but it's not LIF because I didn't even notice. I changed it to LICO. So it's really 42.5-ish because it's 7 grams for lithium plus 35.5 for chlorine. 42.5 grams for LICO. Are we good now? I apologize about that. All right. 42.5. What did you get when you divided that? 4? That's cute. It's like going to the store and they're like, that's $12. You're like, no, it isn't. All right. That's not possible. All right, it's 4. Okay, then what's the kilograms then? The kilograms of this, we have 830 on the bottom, sorry, 0.830 on the bottom. We are going to end up with a number that's not just 4. How much? Okay, that's the molarity. Sorry, molality. Okay. What? No, this was kilograms down here. Yeah, we're going to have to convert to find molarity. No, it doesn't. And I even wrote them. That's why Diane's probably annoyed. The first 2 problems, I put molarity up here and then molarity on the bottom. So she's like, wait, you can't do that. All right, so let's come now to molarity. Molarity is moles per liter. I still have moles as 4, but I don't know my volume. I only know my mass. But I gave you the density, right? If you recall, density is equal to mass over volume. So what's my volume equal to? Volume is equal to mass over density. So what's my mass? No. Oh, sorry, it is 1,000. It is 1,000 because it's the solution. Yeah, I'm failing right now. I chose 1,000, right? So I take my mass and I divide it by my density, which was 0.91, and I end up with what number? 1,090? Is that what you said? Okay, that's a 0. All right, and that's the milliliters, which would really be 1.099. And now divide that, and then you will have your answer. Can't talk. Okay. Tricky, but doable. Yeah, if you have to use molality, the density will be given to you. This one, yeah, like the AP test would have been more clear, but I just made this up on the spot. could have used 100. The real reason I chose 1,000 is because typically if they do this, you're talking about something in water, and that just gives you it in kilograms already. You take a kilogram of water or 1,000 milliliters of water. So, I mean, if we did it with 100, all the math would still give us the same answers. So we just change it tiny little bit. Okay. Now, we have, this is just talking about what we've done, changing molarity and molality. You just have to have the density. Okay. And now let's talk about, we'll come back to these tomorrow, but we need to talk about the last thing, and that is colligative properties. Are we out of here like right now? Okay. Oh, we have 5. Okay. Okay, we can cover colligative properties in 5 very simply. Colligative properties, in a nutshell, are that the boiling point and melting point of a solution are different than the boiling point and melting point of the solvent. It's the reason we put salt on the roads in the winter. All right? It's to lower the freezing point so ice doesn't form as easily. All right? The solution has different colligative properties, which are just properties of a solution, than a solvent. So changes in colligative properties depend only on the number of solute particles present, not on the identity of the solute presence. So that means like I could add NaF or NaCl or KCl or whatever. We don't care necessarily what's in here. We care about how many of them are in there. Okay? The colligative properties are vapor pressure lowering, boiling point elevation, and melting point depression. Osmotic pressure is no longer required, so we don't discuss it, but it does have a great deal to do with osmotic pressure, which you may have learned in AP Bio. So, I think it goes one at a piece. Because of the solute-solvent intermolecular attraction, higher concentration of non-volatile solutes make it harder for the solute to escape the vapor phase. So that's a lot of words. But what it's saying is if you have a solution in here, the water particles are attracted to the solute particles a little bit, right? So that means it takes a little bit more energy to make it go up, which means that the vapor pressure above is actually lower than we would expect because more of the vapor stays in the liquid instead of leaving because it's attracted to the solute. Okay? Next. Therefore, the vapor pressure of a solution is lower than that of a pure solvent. That's the sentence you need. If you got nothing else, that's the sentence you need. I'll pause. Now, we'll come back to that tomorrow probably. This is a lot worse than it looks. It's actually very simple. All right, boiling point elevation and freezing point depression. What? Sorry, it's a lot easier than it looks. It looks worse than it is. How about that? Sorry. It looks worse than it is. This Route's law, you're just going to multiply. All you have to do is find the mole ratio, and this number is given to you. So it's not that bad. We will do it. I thought we'd get there today, but we're not. Okay. Once again, the solute and solvent are attracted to each other. Okay, so that causes a higher boiling point because the liquid is attracted to the solid. And it causes a lower freezing point as well because the solid is attracted to the liquid. So it keeps things liquid over a greater temperature is what it does. And if you write that one thing, then you can get that whole thing right. All right, colligative properties keep the liquid phase over a greater range of temperature. That's what you need to know. Colligative properties maintain the liquid phase over a greater range of temperature. You're welcome. So it's a liquid at a lower temperature, and it's also a liquid at a higher temperature. Okay. So once again, in the winter, but then kids say, oh, that's why I add salt to my noodles, like when I'm going to make things boil. And that's not necessarily true, because people add salt to their boiling water all the time. You don't add enough to change the temperature, because if you put in enough, you wouldn't eat what you just made, because it would be disgusting. The ratio is too high for salt. Okay, I guess I feel like we must be done. Oh, this is so hard, upside down. Oh.